All right, we're getting close to the end of our Unit 4 review. We're going to pick up here with question 16, which has given us a very general graph with no scale, no numbers, so I'm not going to be able to use actual values here for very much. But I have to have the degree and behavior, domain and range, and I have to be able to identify where we're increasing and decreasing generally. It says to assume the graph has the maximum number of turns allowed, and I'm going to use that to help me find my degree first. The degree tells me that to find the maximum turns, I have to take one away. So every turn happens on either a hill or a valley. So here's a hill, here's a valley, here's a hill, here's a valley. So altogether I have 4 turns. So the degree has to be 1 more than that. So my degree is 5. So this is some x to the 5th function. For my end behavior, I don't have a problem with it if you tell me my end behavior with the words that I used in class. So this goes from low to high. But there's another way to write the end behavior that I want you to see and remember because we used it before. And it says, as x approaches negative infinity to the left, x approaches negative infinity. It wants to know what y is doing. So as I move to the left on the graph, my y value is going down. So y approaches negative infinity. It's also going to ask about positive infinity. So it's going to say, as x approaches positive infinity, which is moving to the right on the graph, what is my function doing? As my graph moves further and further to the right, my y values are getting bigger. So y approaches positive infinity. And this is another way to write our end behavior. For our domain and range, we're going to use our good friend Dinks Rowdy. So Dinks is going to chop to the left and to the right and try to find the furthest left and furthest right we can go. But because of this arrow, the furthest left we can go is negative infinity. And this arrow says the furthest right we can go is negative infinity. So I'm going to do an interval, negative infinity, to positive infinity, in parentheses because we can't actually get to either one of those numbers. For my range, or Rowdy, I'm going to go top to bottom. But again, because of these arrows, the lowest I can go is negative infinity, the highest I can go is positive, negative infinity to positive infinity. The very last thing I have to do is I have to show where on this graph I am increasing and decreasing. So I'm just going to erase some of my marks here so that we can more easily see what I'm about to label. All right, let's go ahead and show increasing and decreasing. There's 2 different ways to do this. Either one is fine. I can trace the graph. I'm increasing here because it's going uphill, so I'm going to write increasing, INC to abbreviate. I'm also increasing here and here. The other way I can label that is I can try and cut on my x-axis. I increase all the way to the left of whatever this number is. So I'm increasing this way. I'm also increasing between about here and here on my x-axis. So that's an increasing interval as well. And between here all the way to positive infinity, I'm also increasing. For decreasing, I can trace the graph here and say this is decreasing. I can also find those points here and say the interval between here and decreasing. And then I can also say this part of my graph is decreasing, going downhill. So from about here to about here, I'm decreasing. And there we go. All right, let's go ahead and find the zeros and roots for some functions here. This one has a little bit of a tricky question in here, so let's see if I threw you too much for a loop. We are going to find the zeros and roots for these polynomials. Let's start with example A. To find the zeros, I set this equal to 0 and solve, and we're going to have to do that by factoring. This has a GCF of 3x, so I'm going to factor 3x out from every term. I'm going to end up with x squared for my first term, x for my second term, and negative 2 for my third term, which is a quadratic that can be factored with a t-chart. I have to find 2 things that multiply to negative 2 and add to the positive 1 with the x in the middle. The factors of 2 are only 2 and 1. They have to be opposite signs to give me a negative, and if I want my answer to be positive, I want a bigger 2 and I want to take away 1. So this is going to factor with x plus 2 and x minus 1, but the order doesn't matter. Now my job is to set each one of these equal to 0 one at a time. So if I have 3x equals 0, my x value is just going to be 0 divided by 3, which is 0. So that's x equals 0, and it has a multiplicity of just 1, because it's the only x in this equation all by itself. Up next, I have x plus 2 equals 0, and when I solve that, I get x is negative 2, and it's the only thing that's going to give me that answer as well. Last up, x minus 1 equals 0, which is going to give me x equals positive 1, which also has a multiplicity of 1. So that problem's all done. Problem 2 has no GCF, and it has 4 terms, so I'm going to have to go ahead and factor by grouping. My first group has a GCF of x squared, so x squared times x plus 4. My second group has a GCF of negative 16, and when I factor it out, I get x. This negative 64 divided by negative 16 gives me plus 4. Now, since these match, I can move them to the front, x plus 4, and the x squared and the negative 16 become their own factor. And those aren't completely factored either. That's perfect squares, with x being squared and 4 being squared. So I can factor that as x plus 4 and x minus 4. And then include this x plus 4 from my original problem. Oops, I don't want that. Thank you. Okay, this is now completely factored, and we can find our solutions by setting these equal to 0 one at a time. So my first factor, x plus 4, if that equals 0, then x is negative 4. My next factor is also x plus 4, so I get a negative 4 twice. Then I can do x minus 4 equals 0, which tells me that x is going to be a positive 4, and that one's only going to happen once. This next problem is where we get a little tricky, and if you were able to solve this, I'm super duper proud. If you weren't, it's okay, because we didn't do any of these in class, but we did, I think, talk about it briefly. Anyway, some of my periods we talked about it briefly. It was just kind of a bonus question in there. Don't stress yourself too much. This question probably won't be on the test. You will have to know how to factor these, but you won't have to know how to solve them. The first one you can factor and solve. It's got x squared minus 4, and I can factor that using difference of squares. X is being squared, 2 is being squared, x plus 2, x minus 2. That's pretty simple now. We've done that so many times. The next term, though, is, first and foremost, it's got a GCF of 2. 2x cubed plus 16 has a GCF of 2. So I'm going to take that over here, 2, and I'm going to factor out the GCF of 2. X cubed plus 8 is my second term. Now this 2 that was my GCF, this is getting multiplied by x cubed plus 8, but it's also getting multiplied by x minus 2 and x plus 2, so I can just move it to the front like I would with any GCF for any problem. So far my final answer for factoring has 2, and it has the x plus 2 and the x minus 2, and then it's going to have everything else we get from factoring this, which is x cubed plus 8, which is perfect cubes. X is being cubed, and here 2 is being cubed. 2 times 2 times 2 is 8. So this is a sum of perfect cubes. Remember, the pattern for that is going to be a and b, so in this case x and 2, and then it's going to be a squared, ab, b squared. So a squared is x squared, ab is x times 2, which I'm going to write 2x, and b squared is 2 squared. Here. I'm going to fill in my signs using SOAP, same, opposite, always positive. So same as the original, plus, opposite, minus, and my last one's always positive. Now all I have to do is simplify this 2 squared as the number 4, and this is finished being factored. So the x plus 2 can go here, then we get x squared, 2x, positive 4. Now this is all done being factored. When I set these equal to 0, we're going to see that first and foremost, 2 can never equal 0. So that 2 all the way up in the front does not give me a factor. X plus 2 could equal 0, though. If x plus 2 equals 0, then x equals negative 2. And that happens once and twice. So that has a multiplicity of 2. Up next, I have x minus 2, which could equal 0. So that gives me x equals positive 2, and that only happens once. The last thing I have to solve is this one. Oh goodness, that's not what I meant to do. This one, which can't be factored. And if I have a polynomial that can't be factored that I have to solve, I can solve it using the quadratic formula, which is super exciting. Negative b plus or minus the square root b squared minus 4ac over 2a. If I solve that, I get my x value. Now this is going to be nasty. Like I said, this isn't on the test, so at this point, if you're done watching this video, then you're done watching this video. But if you're curious about these last two answers, then follow the bouncing ball. In this problem, A is the number 1, B is the number -2, and C is the number 4. 1, -2, and 4. Let's fill in the quadratic formula to solve for my missing x values. I should have 2 more x values here because this has x squared in it. All right, so we're going to have negative b, or the opposite of b. b is already negative, so I'm going to start with positive 2. And I'm going to do positive 2 plus or minus the square root of 2 squared. I'm going to go ahead and square that. 2 squared is 4. Minus 4 times a is just 1, times c, which is 4, all over 2a. A is 1, so it's just all over 2. Let's go ahead and try to solve this guy. X is 2 plus or minus, let's see what happens inside the square root. We get 4 minus, 4 times 1 is just 4, times 4 is minus 16 over 2. And this used to stop us. 2 plus or minus the square root of -12 over 2. But this doesn't scare us anymore because I know how to do the square root of -12. The square root of the negative just gives me I. To do the square root of 12, your calculators can simplify a radical for you, or you can go looking for the factors inside. So I'm just going to break up -12 into its factors. It's got a -1 for the negative part, and 12 is made up of 3 times 4, and 4 is made up of 2 times 2, which is a perfect square. So I'm going to take this 4 out of my square root by turning it into -2. Square root of 4 is 2. I'm going to take this -1 out of my square root by turning it into I. So the square root of -12 actually becomes 2i, and the square root of 3 is still trapped inside, square root of 3. So that means that I have x equals 2 plus or minus 2i root 3 over 2. And I have one more thing that I can simplify here. My numerator has 2 terms that both need to be divided by 2, and both can be evenly divided by 2. 2 divided by 2 cancels. This 2 divided by the bottom 2 also cancels. So x is going to be 1, cancels to the number 1, of course, 1 plus or minus 1i, so I'm just going to call that I, root 3. Now we said we had 2 answers, and that's because plus or minus literally means I can separate this into 2 solutions. X equals 1 plus I root 3, and x equals 1 minus I root 3. Each one has a multiplicity of 1, and we have found all of our solutions. That was really nasty. You won't have to do that on the test, but it's fun. I'm going to do the last question in the last video.